Welcome to my individual project, where we investigate the areas of triangle within the confines of one square. First, we take a look at a square that has been divided diagonally into 4 sections, with each area of the triangle equaling 25% of the square. If the end point at the upper right is moved down the right-hand side of the square, the areas of the top and left sections grow, while the areas of the bottom and right sections shrink. Eventually, the bottom and right sections shrink to 0 and the 2 remaining areas make up 50% of the original square. It is important to note that there are going to be at least 2 similar triangles that are opposite each other within the square. You can know the ratio between the 2 different triangles if they are similar and if there are 2 side lengths provided. Say that one of the triangles has a side length of 4 and the other corresponding side length is 1. We know that triangle ABC would be 4 times larger than triangle EFG. And since area is in units squared, triangle ABC will be 16 times bigger in area than EFG. Now let's look back at our original square for this problem. Let's assume that each side length is 1 centimeter by 1 centimeter, which would mean that the area is 1 squared centimeter, which will stay the same throughout the rest of the problem. Now, if the areas are split up equally by 25%, we can assume that each area is 0.25 square centimeters. Now, let's move the first line on the right side of the triangle down so that the height of the smallest triangle is 0.1 centimeters instead of 1 centimeter. Right away, we can see that there are 2 similar triangles in this situation, with 2 corresponding side lengths. We know that the larger triangle's side length is bigger by a factor of 10. That means that the area will be bigger by a factor of 100. In order to find the area of each triangle, we will need to calculate the base lengths for each one within the square. We can figure out the base lengths when we have a given height with the equation as h equals 1 minus x divided by x. In order to get x on one side, this equation can be simplified using algebra, so that the equation ends up being x equals 1 over h plus 1. If we plug in our initial height of 0.1 centimeters into the equation, we will solve for x as equaling 0.9091 approximately. Now that we know x, we should be able to solve for the area of the smaller triangle on the right-hand side of the square. The base length should be 1 minus x for the entire base length of 1, so you take 1 minus 0.9091 and end up with 0.0909 approximately. And the area equation for a triangle is 1/2 base times height. So we can also find the area as we plug in the equation with our height as 0.1 and our base as 0.09091 and multiply that by 1/2 to get 0.0045 squared centimeters approximately. Remember that there are 2 similar triangles within this problem. The left larger triangle is similar to the smaller right triangle that we just found previously in this problem. The side length is 1 as opposed to the smaller triangle being 0.1. And since we have those 2 side lengths, we can remember that the area is 100 times larger. So we can take the area of the smaller triangle that we found and multiply it by 100 to get the area of the larger triangle, which is 0.45 centimeters squared. Next, we will need to find the area of the middle triangle between the 2 similar triangles on the bottom. The height is going to be the same as 1 minus x, as it makes a right angle no matter what length that the height is on the right side. The base is going to stay 1, as it's the x plus 1 minus x, which will always be 1 as it's the side length of the square. Therefore, we can find the area of this bottom square because 1 times 1 minus x, which is 0.09091, times 1/2 equals about 0.05 centimeters squared. The other area that's left over within the area of the square can then be found by adding up the other areas of the triangles and minusing it by 1. So 0.0045 plus 0.445 plus 0.0455 equals about 0.505. And then if you subtract 1 by that, you get an area of 0.495. I then repeated this process with different heights ranging between 0 and 1. Here are the data for those points. And then graph that data, where we can observe general curves that are opposite each other depending on their position within the square. These curves relate to an exponential equation that is based off of the height point on the right side of the square.